what do I want to talk? I will not talk about coding. I will talk about something that has to do with learning, but it should be a fairly familiar picture to all of us who are kind of in information theory, I guess at least many of you. And let me say, it's a real pleasure to see so many familiar faces in here. And the whole message is that machine learning these days is, of course, tremendously successful. The kind of structures being used obviously work amazingly well. But there's no reason to assume, even though they work so well, that that's the only possible structure we can have, or that that's even the most, let's say, energy efficient structure now. So what I want to look a little bit is from an information theory point of view, what it is that we want to have from a structure, from a machine learning structure, in order to be, to hopefully be good. And then the idea would be that hopefully so many of us in the room who have in the past worked on many other structures like finite state models, Markov models, etc., to potentially think about how you could rather than having the structures that you currently have, like transformers and so on, think of other alternative structures and see if we could make them work potentially even better. So what is the setup? The setup should be, very familiar to us. So rather than learning functions, we're learning probability distributions. And so, that's very clear. Sorry, maybe I stay here. Probability distributions. Now, in principle, you can think of any of your favorite setups. All the things I will say come really back to what was done in universal compression and prediction. So, the natural setting would be online learning or batch learning, but I'm going to phrase it right now in supervised learning. You can think of the what's called the realizable case or the agnostic case, but just to be concrete, I think of one case. Okay, I think of the supervised learning, and I think everything was realizable right now, and I'm not going to comment much more further. Now, what it is that learning, okay, we have to find our own probability distribution, right, given these samples. And, what, of course, the loss natural here in this setting, since we learn probabilities, is the log loss. And since everything is realizable here at the end, the loss, the expected loss here will be some form of Hilbert-Weaver divergence. If it's not realizable, it will look a little bit different, but again, it will have roughly this form. Good. So the learner, everything we have learned in the past about this setting, particularly in the online case and in the batch case, that the learner that you should be using in such a setting is some kind of mixture model. Okay, so this means rather than just finding a particular model, you're trying to find a mixture of, remember the p theta, the theta is the parameter in here, and this is general large space. You should find an average of all these learners, and that will be kind of the optimum learner in here. And in particular, this is kind of a Bayesian setting. So the W of theta, it will be some prior on all the models that we have a priori, and you should then weigh them by the posterior. Okay, good. I'll get a little bit back later to what the prior should be. Okay, so now what should we be looking for, right? We should be looking for something that gives us non-uniform regret bounds. Why non-uniform? If in general we had uniform regret bounds, so things of something like VC dimension or many other ones that people have been using, then you will always be stuck with the following. You can either have very large, so everything will be here probabilistic. So we'll see in a second that the regret will be some form of the log of a probability. So either you could have these probabilities for the various models to be all more or less the same size, right? But since they have to sum up to 1, right, then you can only have few models in this space. And so this means you will be stuck with something that is not very expressive. Or you could have something where you have many models, right? But then these probabilities natural, but the packing would have to be small. And then it would mean that you would actually need many samples to learn something. And so this would also mean that no matter what you are trying to learn, even if you're trying to learn something very simple, you would be stuck with the same number of samples that you would need trying to learn something complicated because they're all the same. So what you would like to have is something that looks more or less like this. okay, you would like to see looks like this. Maybe something where you have some models that are considered simple in that architecture and some models that are considered complicated. And of course, hopefully the one that you will try to learn will be one of these that have a large probability and so will be easy to learn and you will only need few samples. Okay, so, let me just, I will later on refer to it. So I'll call this a broad complexity range and that's what you would like to have. Okay, so we saw the bound in principle already before, but it's not very, you cannot really do much. So let us just rewrite it a little bit. And so one way to write it down in a form that is maybe a little bit more amenable is the following. So remember, theta is a particular parameter. For every theta, you will get a particular distribution, okay? And I'll come back to this map a little bit later. So now look at the set, fix an epsilon, and look at the set of all the thetas, such that whatever the distribution that you get for that theta, okay, theta 0 is the one, the true distribution. Remember, we're looking at the realizable case, that this theta gives you a model that's very similar to the actual model that you're interested in. Okay, it's within some epsilon squared parameter. And so, if this is the large parameter space, I'm drawing this as a sphere here. Of course, this will not look at all like a sphere, right? Due to symmetries you have, etc. This will be a very complicated region, but I think it's slightly easier to think of it as a sphere of some particular ratios, epsilon squared. Okay, and so what is then the important principal component of this bound? The component will be the following. So you look at all the models that are similar to the actual model that you have. That think of it as like some spherical region, and you're gonna look at how much of the posterior probability is within that region. Okay, so you integrate this out, and the log of this essentially will be the bound. Okay, the log will be the regret bound that you have. So the regret bound will just be there's an epsilon squared. Okay, so you can obviously trade off. If you take an epsilon that's very large, a lot of the probability will be in there, and then the log of this thing will be small. If you make the epsilon smaller, the probability will be smaller, and what you would like to find is somehow an equilibrium where kind of both of these are roughly of the same size. Okay, so the bound that you actually get will be of this form. And so now if you're an information theorist, okay, so the first thing, the Pavlov's reflex will be, remember, we still have, everything still depends on the prior that we put on this theta, would be to compute what typically we call is the capacity of this case. And the capacity would be that you choose the prior in such a way that this bound would be basically uniform. Okay, it's a min-max approach. You would like to make all of them basically equal, right? And so one of the main messages is do not do this. Okay, this is exactly the wrong thing to do. If you did this, you want to get back to a uniform case, and uniform cases is not what you want to have. Okay, so in our setting, and I completely forgot to the to say this joint work with Meir Feder and Yannick Vogel from Tel Aviv, and some simulations were done by Ido Tal, so apologies for not mentioning this earlier. So the next message is do not choose the prior in any particular way. For us, think of the prior as just being more or less uniform over all the parameters. Okay, it will not play a particularly important role. You will get what you want through the architecture and not by choosing the prior in any particular smart way. Good. Okay, so there's, I'm not going to go through it, but you get this bound by just 2-3 lines. And if you have worked on whatever universal compression or prediction, these are very familiar steps. Good. So as we said, the complexity, okay, the important part will be the log of this probability. Again, picture, you have the actual model, you have the models that are around, you look at how much of the posterior mass is inside, you take the log, okay, that's the bound that you have. Okay, so now the top one where you integrate over the posterior is still maybe not so easy to think about. What's easy is to think about the prior complexity, which is what gives you what's called typically the inductive bias, okay, which tells you how much the model itself biases to certain models to start with. And that's very easy to think about. It's still this epsilon squared region, okay, that's the same, but now you're integrating over the prior distribution, okay, which is relatively easy to do because you just choose this before. Okay, so keep that in mind. It's a prior complexity, and we're going to look a little bit about it. Okay, so still these measures are not, but they're not completely easy to compute, but you can think of some auxiliary complexity measures, meaning things that are kind of maybe easier to think about and potentially easier to compute, but are related to it. So let me just mention two. The first one, it's kind of obvious to think about it in general. So think now, for example, for a neural network of certain width and depth. And it's kind of obvious that there's some functions that are easy to represent and some functions that are complicated to represent, right? You would assume that something that's, let's say, a constant function or some very simple function, you would only need few nodes to actually represent it, okay? And the rest can pretty much float around whatever you want. Versus, there might be some functions where you pretty much need all the nodes to be fixed in some particular degree. There might still be symmetries in there, but you more or less have to fix them, and you can potentially only wiggle them a little bit in order to stay within a model that is epsilon squared close to the actual model that you want, right? So let's assume it was something where you would need all the nodes, right? And each of them you can just wiggle a little bit, right? Then you would assume that if everything is probabilistic and think about that all these parameters live now more or less uniform over some particular range, right? Then you would assume that if you have size, let's say you have d times w, d is the depth and w is the width of nodes, you will assume that the complexity, okay, which is again, remember the log of the probability, let's think of right now of the prior probability, would scale something like proportional to the d times w, because every node potentially, might have to be fixed to something. And now they can just wiggle a little bit, which gives you a little bit some probability, okay? So it would be something like d times w times some constant, which has to do with, the epsilon by how much you can wiggle. Okay, so that might be for complicated functions. But it's easy to think of functions that might be much simpler. Think of, for example, just the zero function or maybe the uniform distribution, right? So that should be a function that's much easier to represent, right? And so, I don't know what's the best way to represent that function is, but one way is we could just make sure that after the first layer, the output, no matter what the input is zero, and then it doesn't matter what the rest is. The parameters can just vary over no matter what it is. If after the first layer the output is zero, okay, then everything will be zero at the output. Okay, and how can we make sure that the output of the first layer is zero? Well, we have the W's at the inputs, we have the bias term. Let's assume the input X is bounded in some particular region. You can just do a little bit some computation to see that if you want that, okay, you get a certain bound on the bias. So now the bias term is in a certain region, okay, and if you think of all the W's and for this particular thing, all the W's in the bias term, and you think you have over that, whatever, let's say rectangle, you have a certain uniform distribution, then there will be a little bit some corner that's cut off, which when this inequality is true. And if you integrate over that, this gives you a particular probability. And so this means that now, okay, if you do this for all the inputs here, you will see that the complexity will be at most W times some constant, okay? And maybe you think of W need to be roughly the same size, so this will be roughly the square root of the complexity that you have, okay? For me, that's the best thing. Maybe there's even, ways to represent this function in another way that you get even a higher probability rather than wrote down. But you can see that there's clearly a range. And how do we get this range? We got it because we used there's a nonlinearity in here, and we got it because we have layers in there, okay? And I'll get back to it in a second. Okay, so good. Now, there's another one when you can think about it. It's based on spectrum. Again, so let's think you're somewhere around the model where you actually are. The probability distribution will be around the actual model that you have. Let's think of them right now. It's simple. Let's think about that. The posterior distribution around it is just looks like a Gaussian. In general, it might be more complicated, but let's think about it. Then we can just take this Kullback-Leibler divergence around it, expand it up to second order terms, and the thing that appears in the middle is just the Fisher information. Okay, and so now you can look at the eigenvalues of this Fisher information and what should happen, right? So you have this distribution, and you want to integrate over the distribution around. You want to see how much probability mass there is. And so, of course, let's just do it locally. There might be many symmetries that you might have to integrate over many. But let's first just think locally, because as long as we have a certain probability that we capture, we get always a lower bound, and that's what we want. And so then what happens, right? So if the eigenvalues are very small, then the expansion around it will be very flat. And if you think of a Gaussian, then you will capture in a small epsilon squared a lot of the weight. If the eigenvalues are very steep, then the Gaussian will fall off very quickly, and you will capture only very little of the weight. Okay, so you can connect how much probability mass there is to how many large eigenvalues, and large means something particular in the scale here there are. And so you can basically get now bound, again, very familiar to us if you think about compression. Okay, so now what is the role of the architecture in all of this thing? Okay, so there are several roles. So the first one is there is, of course, a mapping between the parameter space and the function space, right? So what do I mean? Well, you have the parameters, the thetas, and then each theta gives then rise to some whatever, a function or a probability distribution, right? And so now, depending on what architecture you have, if you think of linear families, then this map typically is more or less injective. Okay, so you have a one-to-one map between the two. And so what this means is that if you're looking at the bound, okay, and you do it around some theta zero, or you do it around another theta zero, then there's essentially no difference in how much probability mass you capture, okay? And if you think of one of them being around, let's say, the constant function or the zero function, and the other one maybe around the degree polynomial of degree 20, okay, it means that you have the same probability mass to capture, okay? So it means you would need the same number of samples that has the same complexity, and it's completely oblivious if you want to learn a simple or complicated function, okay? However, if you think of nonlinear families, let's say a deep neural network, okay, then this will look very different, as we have just seen before. And so this is in general, there's two things that happen. It's first of all a highly non-injective mapping, and why is that? Due to the nonlinearities, right? I mean, certain things can wiggle in a large range, and it doesn't make any difference. And so, this means potentially you can have a very high dynamic range. So that's one way how this plays a role. The other one that we have also already seen playing a role is the layering. Okay, so the compositionality of the map, or the layering of the map, that's in deep neural networks, that's very important. And let me just give you one way how you might see this, okay? So let's first think of the simplest possible case. Let's even forget about the nonlinearity, okay? And people have even done that or already observed. Let's just take one linear layer, right, that represents a particular map. And let's now, instead of taking one linear layer, let's take many linear layers, okay? So you stack them up on top of each other. It's like a deep neural network, but there are no nonlinearities in there, right? And so people have actually done this, as for example, a paper by Aurora and colleagues. And so from an operational point of view, or from an optimization point of view, it makes no sense, because of course, the product of many linear layers gives you just again a matrix, right? And it has exactly the same expressiveness as just one linear layer, so it makes no difference, okay? However, if you think about it, putting a certain distribution on these various layers, and then you look at what the distribution is after you take the product, this looks very different, okay? So one way how you can see it, let's think about it just because it's the simplest mathematical model. Let's think about that you take the entries AI as IID complex entries, and you just normalize them so that they're kind of nice, okay? If you take one linear layer, then the eigenvalues that you will get, they will be distributed on a unit disk uniformly. But if you take a product of many of them, what you will see is that almost all the eigenvalues will be around zero, okay? So this means if you take the product of many, you will get what's called an inductive bias in our setting, okay? That is inductive very much towards simple matrices, matrices that have very few large eigenvalues. Okay. Now that's only, of course you can say, okay, fine, it's a linear layer, and maybe we don't care, but you will get something very similar even in another setting. For example, this is setting now slightly more complicated, where you have the Y's being the composition of many maps. So now you can think of maybe a neural network. And remember, what we want is this Fisher information, this I, okay, in this case. And I'm not going to go through it, but through since it's compositionality, The efficient information has also a recursive structure that will give you some block matrix. And if you look at this, then you can see that, again, you have product of matrices appearing in here. So something very similar will happen also in the real case, for the efficient information. Remember that the spectral bound asks us to say something about the efficient information, and in particular, how many large eigenvalues you have. And so you will see that something very similar will happen there too. Okay, now, so what do we want? We want an architecture that has high dynamic range, okay? We've seen that current architectures like neural networks, for example, have this kind of property due to layering and the non-injectivity of the mapping due to the nonlinearity. However, that's not all you want, right? Because let's assume you had that, but let's assume you had a structure in which the signals that you're actually interested in were exactly those that have very low probabilities, right? Then you would do yourself more harm than you do good, right? You would do exactly the opposite thing, right? So what is the evidence that this is kind of, let me just say, matched to the signals that we're interested in, okay? Now, that's not really a science question because we don't really have a model for what is the signals that we're interested in, but there's still some indication, okay? And what are the indications? Well, very often we're interested in what's called natural signals, right? So this might be signals that, here just some possible explanations. For example, signals that come out from physical systems that sometimes are described, like they say, by PDEs or things like that, okay? And those are naturally, we have smoothness properties. There's also a lot of literature on about the signals that are natural images or maybe speech or something like this. Those would be things that typically represent or have a representation that admits very sparse representation, right? And then the third one is there's a huge literature on this, particularly about approximation theories, that signals that are easily represented by compositionality, so where you take just some very simple operations, okay, and apply them repeatedly by doing this layering or compositionality. Again, natural signals seem to be very well approximated or very well represented by those. And so we would like to have, of course, also an architecture that kind of behaves well under those, meaning if you have something or a combination of those, you would like that means that this signal has a very high probability, has a low complexity in our representation. And indeed, if you look at current deep neural networks, there's a lot of evidence that exactly, again, these three properties are ones that play very well together with neural networks. Compositionality of obvious reason, because it has exactly this compositional structure, etc. Okay, so good. Now, everything, of course, has to do with everything what I said here has to try to do with this particular learner, right? Which is this mixture model. And so now, of course, actually learning this mixture model, you cannot really do, okay? What you can do is you can just run SGD with sufficient noise, okay? And if you do that, then in principle, it would sample from this posterior distribution that you have. I mean, so it would sample from the W theta given S, okay? And so what you can then do, so it basically gives you just samples of this. It doesn't give you the whole thing. What you can then try to do is you could try to maybe learn many times, and that's also what people, of course, have done, right? They have done things like ensemble learning, where you don't just learn one particular structure, but you learn many, okay? And so then you could think of this Q hat, where you have simply a discrete mixture rather than the actual mixture, right? As being an approximation to this learner that we talked about. And sometimes, of course, also you're lucky, and anyway, even you get that this distribution is very peaked, and that even maybe single models might already be fairly good for learning it. Okay. Now, of course, all of this assumes that even though what I said is correct, meaning that it samples from this, of course, you might have to train for fairly long, right? And so I don't think there are very good bounds currently that tell you how long you actually have to train with this noise in order that this sampling from the distribution is a reasonable approximation of what actually happens. Okay. Good. So we ran some experiments trying to see this. So this is an experiment that redoes something. There was a paper maybe, I don't know, 7 years ago or something by Ben Rest and others who did, I guess it was called rethinking generalization. And what is the basic idea that they took something like the CFAR data set, right? And they learn it and you know, with a particular network, I guess the inception network here, and it learned very well, okay, and could also do good generalization. But then they relearned the same network, the same data set. However, what they did is two things. Number one is they mixed up the labels, okay, meaning that the actual labels that come to this CFAR data set were now random labels, had nothing to do with, okay, said car, but was maybe banana or whatever, okay? Or they just randomized the pictures themselves, okay? And the whole point is that now this data set doesn't really make any sense anymore, okay? But of course, the whole point was that it could still learn, okay? It could still, you know, the capacity of this network in the sense that they had was big enough to learn, but clearly it couldn't generalize because, you know, you learned the nonsense, okay? Now, so we redid this experiment. So what would we expect, right? If you think of the eigenvalue of the spectral bound, what you simply expect is that you will get very different eigenvalue distribution, okay? And so indeed, so what you see on the vertical axis are the eigenvalues. On the horizontal, you see the top eigenvalues, so they're all ordered, okay? And now, you know, in principle, this would be very difficult to do because you would have a 1.6 times 1.6 million squared matrix, right? But there are algorithms that allow you to just compute the largest eigenvalues if you just after the first few of them, and you can see we're just looking at the 500 largest eigenvalues, and you can see that for the actual case, right, you get very few, maybe I don't know, 20 reasonable eigenvalues, maybe even fewer, okay? So the model, you know, there's really only very few parameters which define that model for the actual thing, versus if you so it's the bottom one, okay? It's the bottom curve, okay? So you can see there are only very few eigenvalues that you have, versus if you take the two cases that don't really make sense, you get many more, and they have much larger eigenvalues, okay? So, okay, goes in the right direction. I'm not claiming, you know, that this is, and of course, people have done these kind of eigenvalues for many different cases, but, you know, this is in direct connection to the expression that we, of course, have, okay? And so, of course, this is also very much related to what people have observed about flat minima, etc., right? So if you ever seen that, people already, I think, 25 years ago, Schmidt, Hoover, etc., observed that if you converge in your learning towards a point that is around flat minima, okay, then it's generalized well, okay. That basically says the same thing, except the point here is not the point that it's a flat minima that does something. The point is that if it converges to something that has a very large probability, then automatically it must be at a flat minima because it means that there are only very few eigenvalues that are large, okay? So it's not the flatness in itself. The flatness is a consequence of what the bound says rather than just being some phenological, you know, observation. Good. Okay. You know, there are other settings. This is the online, but, you know, let me skip it. The point is that they still look very much the same, the kind of forms. You have the same kind of statements. You can think of the agnostic things to become a little bit more complicated because you no longer have standard Kullback-Leibler things, but you have slightly more complicated expression. But let me skip that. Okay, so what's the summary? Okay, I think if you think about this framework, you know, so pretty much any thing that you would like to on-learn batch, you know, the kind of things that currently are transformers, for example, that are large language things you can model like this. So, you know, all the things that we're interested in, you can model. This will all lead to what you want, I mean, non-uniform and model-specific complexity. And complexity here, what's important to keep in mind, there's no such thing as an absolute complexity of a signal. a complexity is always relative to an architecture, okay? So there could be a signal that's very simple in one architecture and could be very complicated in another one. So it doesn't make sense to just talk about the complexity of the signal in itself, but it just makes sense to think about it with respect to an architecture. Now, so you have auxiliary measures like the spectral one or the counting bound, which are kind of easier to look at, right? Because you can just empirically maybe converge to something, compute these things, and then give bounds. What do these things give? Well, they will show you that there's a certain inductive bias that you get from various architectures, depending on what you have. And this inductive bias doesn't come from by putting in a prior in, right, which you would usually do, but it comes in simply from the structure, from the layering, from the nonlinearities, etc. And you see that this inductive bias comes from first principles. And for example, you see that if you take more and more layers, right, then automatically this would lead to things that tend, for example, matrices that have a low number of eigenvalues, etc. Okay, so in principle, the learner is connected to what we do in practice. Also, exactly how strong that connection is remains to be seen, because you would need actual quantitative bounds. And it has, of course, the thing has, of course, a very direct coding compression interpretation, because the bound is the log of some probability, right? So, of course, the thing that we always think of. Okay, so there's a huge literature. There's no way I can give it any reasonable justice here. Okay, as I mentioned already, flat minimum sharpness, the pace-back bound. Of course, there's a lot of things go back to exactly the universal prediction and compression. Of course, literature, etc. And each of them are, of course, large areas in themselves. Okay, so what would be interesting to do? Okay, so we have only run, some experiments. Of course, people in the literature have done a lot of experiments, but using, it would be nice to do them exactly in a controlled way, according to us, to see how refined we see this eigenvalue distribution reflected by looking at various architecture, changing things, maybe the length, the width, the height, and see how that's reflected, okay, according to what we expect. To really think about how good is right now the claim that SGD samples from this posterior, given that you might have to wait, of course, a very long time. And then you could, in principle, there's a whole literature of people that compute, let's say, VC dimension for various things, or other bounds for various structures. Of course, again, we have a complexity measure here. It would be nice to take architectures and particular classes of functions and then compute, for example, complexities to get a little bit some idea of how they relate, right? And that, of course, you could do a whole industry with that to see, what do you want from the architecture, and how do different architectures favor certain classes of signals and so on, okay? But I think the most exciting thing, okay, would be to look at alternative architectures, right? And again, I said this in the beginning, right? Right now, things like transformers seem inevitable. That seems what people do, and it works. Obviously, it's hard to argue with success, right? However, it's always like this. They seem the only thing in town because that was work. People have done a lot of things, but there's no reason that should be it, right? I mean, remember before ChatGPT came out, right? Google was the inevitable big thing in town, and it was completely inevitable that they would always stay like this. Suddenly, OpenAI came in, and everything changed completely, and it looked like Google is going to go out of business, right? And then within half a year, it's again different. So these things are always, they seem completely inevitable that something stays until someone comes along, changes it, and then it seems obvious that you should have changed it, okay? So there's no reason to believe that transformer is the final answer. We know that they have problems with energy and scalability, right? And people before these things came around, they worked a lot on finite state models, on various Markov models. There's a whole literature on this thing, right? And they were completely wiped out by the transformer guys, right? But, in hindsight, if you know what it is that you're looking for, right? Potentially you could go back, revisit, and see, it's not just about, of course, the performance in itself. It's about all these other measures that we talked about. And, I think there's a good reason to believe that there's other architectures that we could use. And that would still, that might work as well or be even better, right? That particularly for large language models, they are in principle models that are much more suitable, right, from itself than transformers. Just if you think about what they're doing, right? And wouldn't it be cool if one could actually make progress and run, replace NVIDIA? It's only 5 trillion. Why not? Okay. You have to have ambitions, okay? And that, of course, would be nice to do. And that ends my talk. Thank you very much. Any questions?
So in ML architectures, it is very critical to initialize properly based on biases, and there are various things for that. Some more complex, some less complex. Do you account for that in your priors?
So right now, so that has to do with the SGD, right? So exactly, you would have to check how does the initialization, right, then really reflect on how you sample, how long you have to run it, right, etc. So I don't know enough exactly about that, but it's a super important topic, right? And you're absolutely right? That much more has to be done. But I don't know, exactly to what degree we have bounds that reflect of how the initialization reflects then how long you have to actually learn, how long you have to let it run so that the distribution converges to this, right? Because currently, I guess the point of view is often an optimization point of view, which is a little bit different, right? You want to get to an optimum. That's not what we want to necessarily do here, right? But you're absolutely right. Okay.
So your basic setup is very much like a mixture of experts, right? So especially when you were discretizing that, is that the correct understanding?
So that it's fine discrete is just because of our inability to actually compute the mixture model exactly. If you could compute it exactly, you should compute it exactly, okay? But you would assume, after all, there's a whole literature on how taking, averaging over many models, right? That's in general better, and that is obvious from that point of view because that's what you should be doing here, right? But that we do a discretization right now is just due to necessity because, how else would you compute the actual mixture model? Okay, it's not a feature. It's just a necessity.
I have one more comment on the curvature propagation. Because if you want to compute the Hessian of a neural network, which is a stack of nonlinear things, sometimes with attentions, so this graph is more complex, that's one thing. And another one is that the Hessian over high-dimensional tensors, it wouldn't backpropagate in a simple manner. It's not the standard chain rule, which is linear, but it actually has more components. So it's like.
But this expression I showed you, what's for the
I didn't account for that.
Yes.
Okay.
That has exactly already this form. Yeah. So that's in there, right? But of course, it's no longer just. It's a little bit more complicated because it had this. It first of all had components, right? Various components in there, and then also had just products. But then there was something in between, right? There was the Fisher information in between, and then there were the Hessians on the left and right.
Certain activations may help you to early prove most of those components. For example, you have ReLU, which is a very popular kind of wiki ReLU. So piecewise linearity, it kills the propagation of the second order terms.
Okay.
So this entire thing, even if it looks huge in the beginning, can actually collapse under certain activation functions to a large degree. That speeds up computations a little.
If you want to actually, yeah. So if you want to compute it, again, it would be nice now to take architecture, do variation of the architecture, and see what it means for this. But I'm aware there's a huge literature on things, and one might be how to compute it more efficiently. The other one, what does it actually give, right? Because one is just efficiency, the other one is what would be the implication, right?
Other questions? So maybe just a quick one. Do you get when you do universal compression, sometimes you get a bound in terms of the class of distribution, the big theta on the performance, how fast you converge? Do you get some results like that here?
No, because so here, I think if you want it on the class, then this would be again like in the VC, you would do worst case. So the whole thing is we don't want to look at worst case.
So then do you get something in terms of the complexity within the class that you get down?
Just complexity of the actual model that you're learning. So everything else with respect to the actual model that you're trying to learn. Okay.
And you can do it like in general, you need to assume some kind of a model, right? I mean, because you cannot assume everything. Right? So
No, the model is the architecture now. That's it. Okay. So you take a neural network, you take a transformer, you take whatever. That's the architecture, right? Then you in the realizable case, you would pick one of them from there, right? And then that would have a certain complexity. And then you would have the bound is with respect to that particular model inside the architecture.
And the bound would say it's like the complexity of this model plus what would
the bound was exactly this epsilon squared plus the complexity, right? So it's basically, if you choose them roughly the same, it's basically just the log of the probability.